Hello guys, in this video I'm going to go over a few examples on how to solve RLC circuits. Before we proceed, I forgot to mention a few things in the last video. If the damping ratio is bigger than 1, we say the circuit is overdamped, and if the damping ratio is equal to 1, we say the circuit is critically damped. And if it's less than 1, we say the circuit is underdamped. Now, this is an important terminology, so you should be aware of these terms. So the first thing we need to do in solving the circuit is to derive the characteristic equation. Now, we have seen where this equation comes from in the last video. So if we use this equation, the equation we get looks like this. And if we use the discriminant, we can see that this equation has two solutions, which means two roots. And you will find those two roots to be -1 and -5. So since S can have two real roots, the circuit is an overdamped circuit, so we need to use this equation. Now remember, if we have two real roots, the circuit is overdamped. If we have only one root, this is when the discriminant is 0, we have the circuit is critically damped, so we need to use this equation. And when the discriminant is less than 0, the damping ratio will be less than 1, and we say the circuit is underdamped. This is when we have two imaginary roots, and we use this formula in that case. So using this equation, because the circuit is overdamped in our case, our solution will look something like this. The next thing we need to do is to find the value of K1 and K2. And if you can see here, there are two conditions given. V of 0 is equal to 10 volts, and I of 0 is equal to 1 ampere. So to use this information, we need to plug 0 to this equation. And the equation that we get comes in this form. So we have our first equation. The next thing we want to do is to use this information to find the derivative of V of 0. And to do this, we use KCL on this node. And the equation we get is this. And we know that the current across capacitor can be written in this way. So if we replace this part with this equation, and this part using a simple Ohm's law, we can rewrite this equation in this form. We know the value of V of 0 to be 10 volts, and we know the value of the current across inductor to be 1 ampere. And since we also know the value of capacitance, using this information we find the derivative of V of 0 to be -90. So since the derivative of V of 0 equals 90, we need to differentiate this equation to use this information. So if you differentiate this equation, the equation that you get looks like this. And if you plug 0 on both sides, you get this equation. And we know that this is equal to -90. So now we have two variables and two equations. So we can find the value of K1 and K2. If you calculate it, K1 equals -10 and K2 equals 20. So our final answer using this equation comes in this form. Another way to solve this problem is using the Laplace transform. Let's look at the capacitor. Now here I have written the equations for capacitor and the equations for inductors. And if we take Laplace transform on both sides of this equation, the equation that we get comes in this form. Now for this part, I used this equation, and for this part, I used this equation. If we rewrite this whole equation in terms of current, we can get this equation. And from these two equations, we can draw the Laplace version of this circuit. Here I have drawn two equivalent versions of this circuit. I drew this circuit using this equation, and I drew this circuit using this equation. Let's do the same thing for inductors. The equation that describes characteristics of inductors comes in this form. If we take Laplace transform on both sides, the equation that we get looks like this. Now here I've used this formula. And if you rewrite this equation in terms of current, the equation that you get comes in this form. And just as before, we can draw two Laplace versions of this circuit using these two equations. So this goes for this equation, and this circuit goes for this equation. So in summary, if you have an inductor, you can replace inductor with one of these two circuits in the Laplace domain. And if you have a capacitor, you can change to one of these two circuits according to our usage. It's easier to think of this in this way. If you see an inductor, you change the inductance to S times L. And if you see a capacitor, you change the capacitance to 1 over S times C. And you treat these two components as if they were resistors having these values. And if initial condition is not 0, just like in this case, you can add those values in an appropriate manner using these parts. So now let's actually solve this problem. I'm going to apply KCL on this node, but I'm going to write this in the Laplace version. So IR in this case would be V of S over 5, and IL in this case, now using this circuit, it would be V of S over, now inductance changes to S times L, so 6 times S. And since we have initial condition in this case, since initial value is not 0, we have to add this part as well. So it becomes 1 over S. And plus, for IC, we can use this circuit. And as I have mentioned before, capacitance turns to 1 over S times C. So it becomes V of S over 30 over S. And since initial condition is not 0, we have to add this part as well. And if you can see here, this is the opposite of where the current is flowing. So you have to write this in a minus sign. And if you can see here, the direction of this current is the opposite of I of S. So you have to say minus C capacitance times 10. So this is 0. If you rewrite this equation in terms of V of S, the equation that you get is this. I skipped the calculation. The next step is to use inverse Laplace transform to obtain our actual answer. And to apply inverse Laplace transform, you have to change this equation in some form similar to this form. And you can write this equation in this way. And this changes to this equation. And now finally, using this equation, we can apply inverse Laplace transform to this part. And from this equation, the answer V of t in time domain, we get 20 times e minus e to the minus 5t plus, actually minus, because we have minus here, 10 times e to the minus t. So if you can see here, this is the same answer as before.